So in this problem, we've been told, okay, the sum of two positive numbers is 16. And what we're looking for is what is the smallest possible value of the sum of their squares? Okay, well, it sounds like, we don't know several things here, but it sounds like this problem hinges on two positive numbers. And we know that the sum of those positive numbers has to be 16. Since I don't know what the numbers are, why don't we set out and give them variable names? Why don't we say, let x and y be the two numbers? Now they may be the same number, so it's possible that x is equal to y, we don't know, but let x and y be the two positive numbers. I don't know that they're the same, so I have to use different variables because x could be 12 and y could be 4, or vice versa. It's possible that they'll end up being the same value, but we don't know that. All right, so what can we do here? We want to, what's our objective function? In this case, what are we trying to maximize or minimize? Well, in this case, we're trying to determine the smallest possible value of the sum of their squares. So our objective function, basically the sum of squares function, we want to minimize the sum of their squares. And, you can call this function whatever you want. Maybe I'll call it, s. And what is the sum of their squares going to look like? Well, that just means to add together the square of one of the numbers plus the square of the other number. So that might look like, x squared plus y squared. That's the sum of their squares. And technically right now, my sum of squares function s is in fact a function of x and y. Both variables x and y appear in our equation. Of course, when we want to be able to maximize or minimize this, we're going to have to come up with a way to rewrite our objective function only in terms of one of the variables. And typically, we prefer to have that be x. Well, what's our constraint equation here? Our constraint, what are the limits here? Obviously, if we didn't have any constraints, we could just make both variables 0, and 0 squared plus 0 squared would be 0, and that would be the smallest sum we could get. But we have a constraint, and that is that we know that the two numbers have to add up to 16. Okay, so we've got x plus y has to equal 16. And this is nice because now I can take my constraint equation and I can isolate y in order to come up with an expression that I can then substitute in for y in my objective function. So if I subtract x from both sides of the constraint equation, I'm going to end up with the same constraint, but in a different form. And that is that one of the numbers, y, has to be equal to 16 minus the other number, x. So now I'm ready to use this to substitute for y in our objective function. Okay, so what's that going to look like? I'm going to take my objective function, which was a function of both x and y, and I can now rewrite it as just a function of x by replacing y with the fact that we know y is going to be equal to 16 minus x, and thus we're going to have this objective function. What values are going to make sense here for x? Well, if we think about it, we have two positive numbers that have to sum to 16. Well, if they both have to be positive, then x can't be exactly 0 because 0 isn't positive. So I know x has to be strictly greater than 0. And if y also has to be positive, then x can't be exactly 16 because then y would have to be 0. So basically, the values of x that are going to make sense in this problem are values of x between 0 and 16. Basically, those are the only positive numbers that are going to also give me the possibility of y being a positive number, since they both have to add up to 16. All right, well, let's just expand this and simplify our objective function a little bit. So before we differentiate, why don't we just expand the square here. 16 squared would be 256. And I would get a minus 32x and a plus x squared. And if we combine like terms, we're looking at 2x squared minus 32x plus 256. Okay, so now we want to take the derivative of the function. That's pretty straightforward since it's a polynomial. Derivative of 2x squared will be 4x. Derivative of minus 32x will be minus 32. And that's it. And we see, of course, that s prime of x is, again, defined for all real numbers. So I don't have to worry about it not being defined. And so that means I just want to look at where will it be equal to 0. Well, it's going to be equal to 0 if 4x is equal to 32, or if x is equal to 8. So s prime of x will equal 0 when x is equal to 8. Now, again, I want to determine that I know, 8 is a critical number, but is it a max or a min or just a plateau? Well, again, we could do the first derivative test. We could do the second derivative test. We could do both. In this case, I think the second derivative test is going to be, again, even easier than doing the first derivative. So if we do the second derivative test, s double prime of x, if I take the derivative of s prime of x, s double prime of x is just actually going to be 4. In fact, notice once again, s double prime is a constant. This is always positive because it's a constant. So that means that if I plug in s double prime of 8, well, it's still going to be 4, which is greater than 0. That means that our function s is always concave up. Because our second derivative is positive, our function basically has to always have an upward facing bowl shape. Well, what does that mean about our critical number? Well, what we know then is, when x equals 8, s prime of 8 was equal to 0, so we had a horizontal tangent line. And s double prime of 8 was positive, so we had concave up. Therefore, when x equals 8, we have a local min. So that's going to mean that my objective function, in this case, the sum of the squares of these two numbers, is going to be minimized if I let x be 8. Well, if x is 8, then what does y have to be? It also has to be 8. So the two numbers that will give us the smallest sum of squares and we can sort of see this, if we sort of evaluate this for numbers nearby, just as kind of a quick illustration here, if x and y are both 8, then the sum of their squares is going to be 8 squared plus 8 squared, 64 plus 64, which is 128. And notice if you altered things a little bit, like for example, like if you let x be 9 and then y would therefore be 7 so that they could add up to 16, well, then the sum of their squares would be 9 squared plus 7 squared. And if I do that, I would get 81 plus 49. And adding those together would actually give me 130. So I can see that even just in this one little example, if I stray from using 8 and 8, it looks like the sum of the squares does in fact get bigger, right? If I go farther, if I let, what if x is equal to 10 and y is equal to 6? Well, then the sum of the squares is going to be 10 squared plus 6 squared, which gives me 100 plus 36, or 136. We're getting even larger. This guy that we found is the smallest sum of squares given our constraint. All right, okay, so we get problems like this guy. So if we read it through, it looks like we're trying to find the dimensions of the rectangle with the largest area that has its base on the x-axis and its other two vertices above the x-axis and lying on the parabola 16 minus x squared. All right, so you want to sort of, imagine, what am I looking at here? You read it as many times as you need to, start sketching, you're sort of like, what is this all about here? What does this thing look like? Well, let's think about this. So essentially, we're being asked to find the dimensions of the largest rectangle that can be inscribed between the x-axis and the parabola 16 minus x squared. Well, maybe it would help to start by sketching that parabola. Now, let's see. I know the parabola 16 minus x squared is a downward facing parabola because it's the same thing as y equals negative x squared plus 16. So if I remember that x squared basically looks like this, negative x squared looks like that, but flipped over the, x-axis, it's just the vertical reflection of it. And if I add 16 to that, it's just going to shift the whole thing up 16 units. So it's going to basically look like that with its vertex at 0, 16. Now, if that's not, obvious to you, you can do a little bit more work to kind of confirm that. But essentially, this is going to have a y-intercept of 16. What's its x-intercepts going to be? Can I determine where its x-intercepts are going to be? Well, maybe if you know the shape of a parabola, that's probably pretty clear. But if not, remember, you can set y equal to 0 and solve for x. And if I do that, I get x squared has to equal 16, which, be careful, you have to acknowledge the plus and the minus here. X could be positive or negative 4. So we've got x-intercepts at negative 4 and at positive 4. And our parabola looks something like this. Okay. So now we want to determine what is the largest rectangle that we can inscribe, meaning sort of fit between the x-axis and this parabola. So I'm basically imagining myself kind of drawing a rectangle in here, such that the base of the rectangle takes up part of the x-axis and the corners of the rectangle above the x-axis are on the parabola itself. And I'm wondering, basically I'm wondering, what's going to give me the most area? Like, for instance, should I make the rectangle sort of skinny and tall? Is that going to maximize area if I have a rectangle like that? Or is it going to maximize the area to make it sort of wide and short? Or is my area going to be maximized if I sort of split the difference and do something kind of, in between? We're not sure, but we want to create the rectangle that has the maximum area. All right, well, in order to think about that, let's kind of draw in a rectangle, and we don't know its dimensions, so those are going to be sort of what we're ultimately trying to find, but we'll draw in one just so we have something to label. So let's say I draw in one that looks like this. Of course, this may not be our optimal rectangle, but let's just pretend that it looks like this. And let's see if we can now kind of label some of this so that we can write our objective function. Well, what do we know? We're being asked to find the dimensions of this rectangle. So basically, I'm being asked to find this and this. I want to find the length and the width, or the base and the height, however you look at it. How should I go about, what should I do as far as labeling them? Well, I could call this side X and this side Y, or I could call this L and this, W or B and H or whatever you want. But here I want to actually do something slightly different that may make our lives a little bit easier in the long run. Now, maybe instead of calling this X, maybe I want to think about, since I am on the coordinate plane and X has its own meaning on the coordinate plane as sort of the horizontal coordinate, maybe I actually just want to think about like this right here being the horizontal coordinate X. And since this is a rectangle, then this guy over here should be just at the negative X value. So this is just a point on the X axis that I'm just going to call X and call this one negative X. And if I do that, then the distance really from here to here would be a distance of X units, whatever X is. X could be 2 or 3 or what have you. And the distance from 0 to negative X is also a distance of X units, which means that the base of my rectangle could be expressed as having the dimension 2x. Okay, so what else do we need? We need the height of our rectangle. Why don't we call that guy y, since y does, if this has a height of y, that is in fact what y represents on the coordinate plane. So I'm just going to say, let's let this value here be called y. And if I think about this now, what's my objective function? Well, what's the thing I'm trying to maximize or minimize? In our case, we're trying to maximize the area of our rectangle. So the thing I want to maximize is area. Well, how would I get the area of this rectangle? I would multiply length times width. In our case, what is the length of our rectangle? It's 2x. The height of our rectangle, or the width, is y. So right now, of course, once again, our area is a function of x and y, and it's just 2x times y. But we'd like to be able to write it as just a function of x. So what's the constraint in this problem? It doesn't sound like that we've been given some kind of requirement that they, have anything in particular, or they can't exceed something. But the constraint in this case is that we know that we're hemmed in by the parabola. And we know that the vertices up here and here have to be on the parabola y equals 16 minus x squared. So what does that tell me about the coordinates of this here point? Well, I know that I could say this point has coordinates, x comma y, based on how I've labeled my picture. I've decided to call this value, just x, and the height is y, so this would have a height of y. Can I replace y with an expression involving x instead? Well, yeah, since I'm on this parabola, remember that the equation for the parabola is the equation y equals 16 minus x squared. That means for any point on this parabola, whatever the x coordinate happens to be, the y coordinate has to be 16 minus the x coordinate squared. That's what the y coordinate is on this graph. So therefore, I can say that this point right here has coordinates x, comma, y, but I can replace y with the fact that y is always equal to 16 minus x squared on this parabola. That's always going to be true about y. That's the definition of this graph. So my constraint is really the fact that, hey, I know on the parabola y is equal to 16 minus x squared. Perfect. I'm ready to plug this in to substitute for y in my objective function. That's going to give me an objective function now that is only in terms of one variable x by replacing y with 16 minus x squared. All right, so let's just distribute to get our area function into a nicer looking form for which to differentiate. So I get 32x minus 2x cubed. And now we want to find the critical numbers of the function. So we've got the function we're trying to maximize. It's now in terms of one variable. Let's find the critical numbers. Once again, this is defined for all values of x. So we can see that a prime, oh, sorry, we have to first take the derivative. Before we get into what a prime is defined out, first we need to find a prime. So our first derivative, a prime of x, will be 32 minus 6x squared. And we can see that a prime of x is defined for all real numbers. So we just want to determine where is a prime of x going to equal 0. Well, we could try to factor this guy, but it's not a super nice factorization, because although I do sort of have this, binomial here, and I might try to write it as a difference of squares, which you could, although they're not perfect squares, they are the square of square roots. But it may be easier just to solve this using the square root property. So if I add 6x squared to both sides, I get 6x squared is equal to 32. Divide both sides by 6, we get x squared is equal to 32 over 6, which is the same thing as 16 over 3. And now I take the square root of both sides, and I just want to remember here that when I square root x, I do need to acknowledge that x could be positive or negative, and that's going to mean we end up with x is equal to plus or minus the square root of 16 thirds, which is the same thing as the square root of 16 over the square root of 3, or plus or minus 4 over root 3. Now, if we look back at our picture here, notice that we defined x to be the coordinate on the right-hand side of the y-axis, such that this was a distance of x. So that's going to mean that our negative square root actually doesn't make sense in the context of this problem, since x is clearly going to have to be a value between 0 and 4. Basically, we're going to have x has to be between 0 and 4. We can see that the only one of our solutions that's going to be a critical number that makes sense is that in this interval is going to be the positive version. So I get x is equal to 4 over the square root of 3. So that's our critical number. And now we want to determine whether that critical number is a min, a max, or neither. And again, to do this, we could either do the first derivative test. We could factor the first derivative slightly. It's not going to factor super nicely, but you could basically try to make it work as best you could. Or we could do the second derivative test. In this case, again, I'm thinking the second derivative test may be actually faster and easier. So I have the first derivative of the function right here. We know that the first derivative was 32 minus 6x squared. Let's use the second derivative test. So if I take the second derivative, a double prime of x, well, the derivative of 32 is going to be 0, and then the derivative of minus 6x squared is going to be minus 12x. And therefore, if I take the value of the second derivative at 4 over root 3, now remember, you don't need to know the value here. All you need to know is the sign. Well, what's going to happen if I multiply a negative 12 by a positive 4 over the square root of 3? This is going to be a negative number. I don't need to know what number it's going to be. All I need to know is whether it's positive or negative. So, because we know that a prime of 4 over root 3 is equal to 0, meaning there's a horizontal tangent line at 4 over root 3, and a double prime of 4 over root 3 was negative, meaning we have a concave down function at that value of x, that's going to mean that x equals 4 over root 3 is the location of a local max, right? If I have a horizontal tangent line and concave down, I've got to have a local max. So what does that tell me? It tells me that the area of this rectangle is going to be maximized if I let this x coordinate right here be at 4 over the square root of 3. Now, I want to be careful to answer the actual question, though. The actual question was to find the dimensions of the rectangle. So I do need to kind of go back now and say, well, what are the dimensions? If this is 4 root 3, then the dimension on the bottom, remember, was 2 times whatever our value of x was. So our dimensions, well, the base was, if we recall, 2x. So the base of our rectangle is just going to be 2 times 4 over root 3, or 8 over root 3. Now you can rationalize that. I'm not going to bother doing it since I think you guys are all comfortable with that. It doesn't really matter in this case. And what else do we know? We know that the height of our rectangle was equal to y. And remember that y was equal to 16 minus x squared. So that's going to mean our height is 16 minus 4 over the square root of 3 squared. And if we just do this out, we're going to get 16 minus 16 over 3. Get a common denominator, we get 48 over 3 minus 16 over 3, which is going to give us 32 over 3. So the dimensions will be 8 over root 3 by 32 thirds.